So our next speaker is Dr. Minje Park, who received his PhD in computer science from the Korea Advanced Institute of Science Technology. He's going to be speaking on object tracking, specifically approaches and applications. Interesting part of this, recognition is certainly one part. Tracking is certainly very different, and the fact that tracking can reduce power and other things is something I'm really looking forward to hear about. All right, let's thank our speaker.
Okay, thank you for your introduction. So in this presentation, I would like to explain the importance of object trackers in computer vision applications and what kind of different approaches exist in real-world scenarios. So here is a brief outline of my presentation. I will start by explaining why we need trackers and what kind of different approaches exist both from algorithmic design perspective and application design perspective. And then I will introduce some important concept of temporal and spatial scheduling, which is very important when you combine some detectors and the trackers. And lastly, I want to briefly mention about the recent advances of deep learning to enhance the trackers. So there are two main reasons why we need trackers. The first reason is to exploit the temporal coherence in video frames. So we all know that recent advances of the object detection shows some great progress in visual analysis, but still, detection is generally slow and it's generally unstable across frames. And the second reason, which I think is more important, is identity preservation. So, because if we can keep track of the identity across the multiple frames, we can do a further analysis or more advanced analysis or more accurate decision based on that thing. But detection doesn't know correspondence between frames because detection is class specific, it's not instance specific. So before jumping into the main agenda, I want to briefly describe what kind of object trackers exist from algorithm perspective. So when we say the object trackers, there are actually many possible implementations. So for example, maybe we can use some point-based methods like a particle filter or Kalman filter, or maybe we can use some patch-based method like template matching or mean shift or tracking by detection method, or maybe we can use more recent and advanced trackers based on the kernel-based methods like the kernelized correlation filter or Moshel filters. So each of these algorithms this object detector algorithm has its unique characteristic and accuracy and performance characteristic. So this presentation is not intended to explain each of them, but focused more on how we can use this kind of trackers in computer vision applications. So from application design perspective, what really matters is the characteristics of the trackers, and especially for how long we can use these trackers. So from this point of view, maybe we can categorize trackers into three different ones. The first one is the short-term trackers. So in this case, we assume that some tracker accuracy is some below than these object detectors. And the second one is the long-term trackers. So in this case, we assume that we have a very strong trackers compared to the detectors. And the last one is zero-term tracker, which is also known as multi-target tracking. This is designed for, you need some scalable solution for the very complex scenes. So I will explain each of them in the next slides. So let's first start the simplest one, the short-term trackers. So in short-term trackers, we assume that first detection is fast enough for regular and quick recovery. And the second, we assume that the tracker doesn't have some self-recovery mechanism. So in every tracker suffer from the drifting problem. So because the tracker is inherently formulated as some incremental update. So the error is accumulated, so we need to reset the trackers if necessary. So the simplest approach to handle this kind of problem is just use the detector as some regular resetting mechanism so that the error is not accumulated in the long run. So this figure illustrates some typical example of the short-term trackers. So we can use just the detection in some fixed interval, and in between those frames, we can use any kind of some simple trackers just to fill the gap. So this seems naive and too simple, but it's very straightforward and applicable for many use cases, especially for the face recognition. So in face recognition, because the face detection is listen to face detection shows a very robust and accurate result. So we can more rely on the detection rather than tracking. So we can use a very simple tracking like a Kalman filter or just template matching to fill the gap to maintain the identity. So obviously drifting is handled by the detector resets. So this is the simplest form. And the next and the more interesting tracking is long-term tracking. So in this case, we assume that the detection is slow or unstable across frames, and we also have some auto-recovery mechanism from the trackers. So to the auto-recovery, we need to keep track or keep updating the internal representation of the current target from the tracker side. So obviously, drifting problem is handled by the model update of the tracker. So as you can see in these figures, the detection is only used at the very beginning of the frame, and most of the remaining frame is handled by the trackers. And sometimes tracking fails. The tracking itself tries to find the object based on its internal representations. So as you can see here, the important part is the self-recovery recovery mechanism. So to do that, we need some quality of the current tracking. So we need to decide the current tracking is good or not. So, but fortunately, most of the listen tracker provides some metric or some confidence value for the tracking score. So let's look into more details about the long-term trackers. So this is some typical state transition metrics when you want to combine the detectors with the trackers. So maybe we can start with the full detection at the very beginning of the frame to initialize the targets. And the target is initialized, it sends the information to the trackers so that trackers can keep the track of the object and update the position as well with its own confidence threshold mechanism. And if tracker fails, it sends back to those information to the partial detector so that the partial detector can search the local regions and maybe it can find the lost target in the nearby regions. So the partial detector is essentially almost the same with the full detection, but it's just a local search. So if the partial detector success, it can send the information back to the trackers so that the loop continues. But if the partial detector also fails, the system decides the target is completely lost, and maybe we can start the entire state transition from the scratch. So as you can see here, we have lots of choices, several choices of each module, and we also have several choices how we can make the criteria about the state transition. So this provides you design flexibility. So depending on your application and depending on your choice of the modules, and also to make some concrete model, you need your domain knowledge about your applications. So this is some example implementation of the modules. Maybe we can use some fast RCNN or SSD for the full detection, and maybe we can use some kernelized correlation filter for the tracking modules, and maybe we can use just RCNN for the cropped region as a partial detector. So if you understand where of each modules and if you understand where about your target applications, so you can make a transition criteria based on that. So the short or long-term tracking, so it's a little bit classic way, but it's still powerful. But there is one critical problem from the system design perspective. If your target application is something like in the left side, then maybe everything okay. But because the single target trackers are fast enough, it's typically less than 1 millisecond per single target. But if your target application is something like in the right side, the tracker performance becomes one of the bottleneck of the system design because there are too many concurrent objects. So keep updating the state transition for each object. It consumes too much time, so it's not scalable to the scenes like this. So we need another solution. So the gyrotome tracker, also known as a multi-target tracker, is especially designed for that. So to simplify our discussion, let's assume that the detection performance is good enough. So we just want to use some identity preservation from the tracker side. So if we assume that, so we can learn the detection at every frame, and we can learn the gyrotome tracker at every frame to keep the identity. So this design is very good for the robust system design because it uses some fixed compute resource which is agnostic to the number of targets. And also the gyrotome tracker is especially designed for the identity preservation. So it finds some globally optimal identity assignment for the all concurrent targets. So the bottom figure illustrates some typical process of the gyrotome trackers. So at some frames, you already find some boxes and identity. You already assigned some identity to each subject. And at the next frame, there are some candidate locations and you need to match those previous IDs into the newly found positions. So to do that, you can make some complete confusion matrix or similarity matrix based on the similarity score, and you can find some optimal correspondence based on that. So every multi-target tracker is designed something like this, and you can use as gyrotome trackers. So in short summary, there are two main approaches when you combine the detection and the trackers. The first approach is you can use spaced detection with a long or short-term tracking approach. So this is a classic way of combining detection and tracking, and the overall system performance is dominated by trackers. So this is still useful for a small number of concurrent targets. So depending on your application, you can take this approach. And the second approach is use the per frame detection with the gyrotome tracking. So obviously, its overall performance is dominated by the detections, and it's quite useful when the number of concurrent target is changing or large. But in both cases, we assume that the detection is reasonably fast, but it's actually not, especially for the higher input resolution cases. So we need something to handle with those slow performance of the detection. But we can, to do that, we can trade off between the latency and the frame per second by distributing detection computation into several frames. The simplest approach is temporal scheduling. So you can just distribute one detection computation into several frames so that it can learn the entire detection process into the multiple frames to meet the system requirements. So the main advantage of this temporal scheduling is the simplicity, because it's very straightforward to implement. So if you, depending on your applications, so you can, this temporal scheduling enough for compensating your slow performance of the object detectors. And the other possible scheduling approach is a spatial scheduling, because in the 2D image or videos, we have one more dimension than the time domain. So we have a better flexibility when we use the spatial scheduling. So the basic idea is same. So we can make a trade-off between the latency and the frame per second by processing the image subregions. So you can have a lot of flexibility when you define the subregions of images. For example, if your target application is some surveillance camera looking into the long hallway, so there is some fixed location of the newly appeared object and the disappeared object. So in between those hallways, you can use the object trackers. So you can have a lot of design flexibility. So this figure illustrates an example of distributing the processing of a single frame into 5 frames by subdividing something like this. But there is also some disadvantage or some pitfalls when you use a spatial scheduling because it requires some subdivision of the space, so it limits your detector performance, or maybe it can limit the maximum possible size you can use when you use the detectors. But that kind of problem also tackled by if you adapt the image pyramid approach when you do the spatial scheduling. So in between those the different subregions, you can use tracking algorithms to fill the gap. So let me briefly show about what kind of approach is possible for the partial detections. So before I finally show some example implementation of the detection and trackers. So partial detection, if you use some past RCNL or SSD-like algorithms, so actually the most recent object detectors actually has some regression capabilities. So, for example, RCNA shows a good regression result on already cropped regions if there is enough temporal coherency. So, in this, you can use the previous result as an initial guess or proposal for the object detectors, so that the object detectors can update its position based on that. So RCNN, SSD, or any kind of some object detector at least can do this. So you can use as something like trackers, especially designed for the updating the position. So let's put it all together. So this is some example implementation of the spatial scheduling and the full and partial detection and the multi-target tracking for scene with the dense subject. So in between those some subregions, the partial detection can handle the targets until the next call for the same subregion IDs, and the multi-target tracking keeps the subject ID across the frames. So of course we can add some temporal scheduling or other kind of some long-term mechanism into the application. So because it makes it too complicated in this slide, so this is just some one example implementation of the putting it all together. So depending on your application and depending on your some system requirement, you can use or mix the techniques I've mentioned here. So let's see some example result of each of them. Work. So this is the simplest case. It's the face recognition. So as I mentioned before, because face detection is very reliable, so we can use some short-term tracker approach. And more fortunately, so because the face recognition itself provides us some robust ID for the identity preservation. So this is the simplest form of the combining the detection and the tracking. And the next is an example of the long-term trackers. So in this case, we initialize the target manually, but you can use any kind of detectors to initialize targets. So after the initialization, the tracker handles the update of the position and the IDs and actually update of the bounding boxes as well. Because the bounding box is updated by the trackers, so actually it doesn't fit well. So maybe you can use object detection regularly to fill the gap. And this is a more interesting and complicated example why we need some complex and powerful trackers. So since if you want to install the surveillance camera in the scenes like that, so there is a lot of occlusions, and there is the target subject change its appearance and the texture a lot. So you need some mechanism to keep the ID of keep tracking of some specific target subject. So in this case, the object tracker internally keep update its representation so that it can robustly find the target subject in the entire sequence. And this is example of the gyroton tracking. So for the people counting, so we combined fast RCNN with a gyroton tracker to actually precisely count the number of some subject or number of people at some specified regions. Because in this case, the target is large enough, so we didn't use some scheduling methods because the input size, we can reduce the input size a lot so that the detection performance meet the system requirement. But in this complex scene cases, so we need some kind of scheduling depending on your some platform performance. So we combined all the scheduling and the gyroton trackers and the partial detections and some object we use the long-term trackers for the compensate of the occlusion or something like that. So before concluding, I conclude my talks. I want to briefly mention about how we can use listen deep learning to improve the tracking algorithms. So the core of the tracking is the compare the two patches. So and compare this patch is similar enough or this patch is different. So to do that, maybe we can use some deeply learned features, for example, trained by the ImageNet classification, so that it can replace the previously handcrafted features, which is generally used in the object trackers. Maybe we can get some more accurate result in the patch comparison. And more interesting, maybe we can use a metric learning approach to find the best distance metric or image patch comparison depending on your domain knowledge if you have enough number of training data. And the second more interesting approach is formulating the object tracking problem as some reinforcement learning problem. So the reinforcement learning is we assume that there is some basic rules of a play or basic rules of actions. So in tracking approach, actually, we can define a very concrete set of actions for reinforcement learning because tracking itself, maybe we can define some translational movement, and we can also add some scale movement, rotational movement, or maybe we can add some stop as one of the possible actions for the trackers. And after we define those kind of actions, we can apply the reinforcement learning as the video frame as the environment, and we can use the success and the failure tracking as some reward mechanism of the reinforcement learning. So based on this formulation, maybe we can use some completely new design when you want to combine the trackers into your computer vision applications. So in summary, trackers provide you with the design flexibility. So even if recent advances in detectors alleviate the needs of these trackers, but still from the performance perspective, the tracker is a very good choice when you actually design some real-world applications. And to do that, you also can apply the temporal or spatial scheduling with the proper implementation of detectors. So it provides us some robust and scalable applications. And lastly, so deep learning-based tracking algorithm more accurate and robust. So again, depending on your application, you can adapt this kind of approach if you want a very strong trackers in expense of your system resource. So this concludes my talk, and thanks for your attention.
Questions? Go ahead.
So a lot of the examples that you showed were from still cameras. How does the problem change when the camera itself is moving?
Basically, it doesn't change because the applications I am currently working is a surveillance camera, so it's mostly fixed. But I think there is no change. Yes, basically, you can apply all those techniques into the camera is changing.
Got it. And my second question was regarding the partial detector that you had. Was there any case where you used a classifier instead of a detector to maybe use that for a faster partial detection?
Yes, partial detections, basically you can use any kind of detectors if that detector has some capability of regression. So, but the classic detectors actually doesn't have that kind of capabilities, but recent deep learning detectors actually have some regression capabilities, so you can use that capability as a tracker.
Sorry, going back to the earlier question, with the moving cameras, the frame rate plays a very important role, right? If you don't have frame rate and the camera is moving, then it will be very tough to...
Yes.
So in your experience, what frame rate, when the camera is moving, were you able to track correctly?
So maybe I can answer that in a different perspective. So most of the object tracker has object tracking algorithm or detection algorithm has some limited regression capabilities. So in these cases, we assume that at least 50% overlap exists in between frames. So depending on the object size, its speed, and the frame per second. So if there is some 50% overlap, maybe we can use them.
Thank you.
Yeah.
Thanks a lot for your talk. One question came to my mind. Are you using any motion models, and do you see a gain when using motion models?
So some tracking algorithms uses motion model to enhance the trackers. So we can clearly get some boost from the algorithm design perspective. And from different design perspective, maybe we can use some motion model or multi-frame inference as a part of the detectors. So recent detectors use some aggregated frames to decide the detection. So actually in that kind of multi-target inference or multi-frame inference or multi-frame detectors, actually it contains trackers as into the detectors. So in that case, there is no need for the external detector for accuracy perspective. But again, the performance perspective, the multi-frame inference consumes a lot of resource. Maybe we can use some classic way of tracking into your system, depending on your system requirement.
And the second question that I had, the measurements, do you consider measurements in 3D or really pixel level measurements? Where do you see more robust outputs?
From the robust perspective, so definitely some measurement in 3D shows your advantage. But it consumes a lot of compute resource compared to the 2D case.
Thank you.
Right. Time for one more question.
So with these systems, if you have the particles or objects overlap with each other, do you end up having to train that on your network as well, or does that change how the network training is done?
So you mean the network is the detection network, or?
Yeah, the detection network.
So the fast RCN or some neural lab-based detectors actually have a very good and partial detection. That means that there is a severe occlusions actually can detect the targets, but the real problem is actually how you can match the full body and the partial body. So you need to have some comparison methods to compare the full and the partial detection to adapt your detectors into the tracking framework.
So I lied, last one. So it's,
Thank you for the presentation. Yeah, just one question. So in your talk, you said that you apply the tracking if there is an overlap between the frames, I mean the object within the frames. But at the same time, in the real world, we get just like sometimes small objects with fast-moving objects. So they are fast-moving and at the same time small objects. So how would you handle that type of problems?
Oh, yes. The 50% is our choice for the demonstration or implementation. For some trackers, which is strong enough, is actually search the very large regions to keep tracking of the crack of the baseball or tracking of the soccer ball or something like that. So depending on the algorithm choice of your trackers, and it can actually handle. So in our case, because the 50% assumption works, but for maybe different assumption of the overlap works for your application. Yeah.
Okay, so do you have any, open source implementation of what you use, or?
So there are lots of some object tracker implementation in open source. So OpenCV already contains some famous, a lot of some object trackers, and I believe there is some reference implementation in GitHub depending on the algorithm design. But this combining the tracker and detectors, I don't think there is some concrete open source implementation.
Yeah, so we had some similar problems actually, just like combining the trackers and detectors for this type of problems. Yeah. So.
Yeah, we don't see some open source implementation for that.
Okay, thank you.
Speaker again. Thanks.